I hope everybody is fine. Well, we have come to the end of our computer networks course, and we are left with certain protocols that come in application layer. By now, we know the main reason why we have application layer, what are the reasons of it, what are the services that it provides, and also we saw that how application layer helps in transmitting the data from an application to a lower layer such as the transport layer. TCP/IP combines the application presentation as well as the session layers together. So we discussed about uh, the chart that is given here, which does a comparison of different applications and with respect to these applications, whether these are loss tolerant or not, how the throughput is to be seen, as well as whether they are time sensitive or not. We also saw the chart in which there was an application and the application layer protocol with respect to that with the transport layer protocol. For example, we saw for email, MTP is the application layer protocol and the transport layer protocol is TCP. Then we saw an example of application layer protocol as HTTP. We also saw how HTTP sends a request and gets a reply. We also saw the difference between persistent and non-persistent HTTP. This was the HTTP request format as well as the HTTP response format. Within the formats, there were codes which was given in status line, which we know as status line protocol, the status line protocol code. These are the ones which are the status codes 200, 300. We also took that as well. Then I told you to try telnet, which was within the lab, and based on that, you would have got these replies. So for today's class, all right, then it gives an example of proxy servers and web cache. What is caching? You can have a look at that. HTTP2 as well. Okay. So for today, first we'll be taking the email service, which basically is SMTP, Simple Mail Transfer Protocol. There are three components which come within this email services. The first one is the user agent, the second one is the mail servers, and the third one is actually the protocol that is known as SMTP, Simple Mail Transfer Protocol. Now, this SMTP is a communication protocol for electronic mail transmission, which in short we call as email transmission. It is an internet standard by now. Okay, it's widely used, most commonly used. We know by now about that. Why? Because it's been there since long. How much? It's since 1982, and I believe most of you might not have been born by then. It comes under RFC 821. For those who joined late, I'm discussing presently about SMTP, that is Simple Mail Transfer Protocol. That is what helps us in email services. Then obviously from 82 RFC 821, it got updated. Then we had 2008 RFC 5321. We have extended SMTP, which is actually the present one that we use is an extended SMTP, which has variety of other protocol added to it. In addition to this, if you have mail servers, if you use other mail transferring protocols or apps, they all have basically SMTP to send and receive mail messages. There are some proprietary systems for mails like Microsoft's Exchange, IBM's Notes, webmails such as Outlook.com, Gmail, Yahoo. Okay. Internally, they might have their own protocols that they will be using, but all of these use SMTP when sending or receiving mail from outside their own systems. And the SMTP uses the transport layer protocol, which is TCP, that is Transmission Control Protocol, typically on port number 25. And for this, there are user level mail clients. So you would have an incoming mail service, you will have an outgoing mail service for those. There are other protocols like IMAP. Let me just write it down. And POP3, where IMAP stands for Internet Message Access Protocol. This is used by email clients to retrieve email messages from a mail server over TCP IP connection. And number two that I just mentioned is POP3, POP3. That is short form for Post Office Protocol version 3. This POP is again an application layer internet standard protocol, which is used by email clients to retrieve email from a mail server. And the present one that we have is version 3, which is most commonly used. And again, POP3 uses the lower stack of TCP IP to retrieve these email messages. There are some differences. There are differences with respect to the applications that we use and so on. Now coming back to the slide here. So user agents, mail servers and SMTP protocol are the three major components for email services. What is a user agent? It's a mail reader. It's like your phone's email client where you start writing the mail, all right, from the inbox where you compose the file. That is what user agent is, where you can type in a mail, you can edit, you can read and so on. That is what we have as a user agent. The second thing is mail servers. This is actually where this is actually where your mails reside. This is actually where you will keep your, once you send it, you check your inbox. This is where your inbox would be. That would be within the email server. So your mailbox basically, where you queue your messages, they are within your email server. You go to gmail.com and you retrieve your messages. Gmail.com is where your mail servers are. And the third part that we have is SMTP. So a protocol between mail servers to send email messages, like a client retrieves a mail or sends a mail, client retrieves from the server. This is all done with the help of SMTP protocol. Like I mentioned, the underlying protocol that we have is TCP with port 25. On the right hand side of this slide, you can see here that there are user agents, They connect to mail server to other mail server. For example, you are sending from Gmail to Yahoo, right? And then you have another user client here. They all use SMTP as the protocol for communication of electronic mails. Then we have the next one, that is the TCP, that's the underlying protocol with the port 25. And in order to transfer the email that we see here using SMTP, since it uses a lower layer protocol, that is TCP, which is a reliable transfer service. So we have three phases of transfer here. The first one is handshaking, that is the greeting. The second, we know that in TCP we have this as three-way handshake. The second one that we have is transfer of messages. And once the messages are transferred using SMTP, you have the closure of the uh, channels, closure of the communication. So the command response interaction is like HTTPs. It uses ASCII text. Then you have response code with respect to it. Here is an example. So we have on the left extreme Alice, who wants to compose an email message and is sending to Bob on the right hand side with the address which is mentioned here, bob@someschool.edu. Once it has composed it, so Alice's user agent sends the message to her mail server. Okay, for example, you are using Gmail, it sends the message to the Gmail server, and the message is placed in a queue within the Gmail server. Gmail server being Alice's mail server. Then the third step is the client side of SMTP opens TCP connection with Bob's mail server. This is the step here which is shown here. And then the SMTP client sends the message that the Alice had written over this connection to Bob's server. Bob's server receives the email message and puts it in the Bob's mailbox. And then when the Bob logs in to his computer, to his email, he retrieves these messages from his inbox. And once the messages are retrieved from the inbox, he would get to read these emails that were sent by Alice to him. So let's say on the left hand side, his email server was Gmail, Bob's was Yahoo. So we had SMTP all between them, creating TCP connections to transfer the message sent from Alice to Bob. I hope this is clear. This is the example of SMTP interaction that we have here. Okay. Now we have a comparison given between the two protocols of HTTP and SMTP. We know HTTP typically used for browsing and SMTP is for mail checking. HTTP uses pull mechanism and SMTP uses push mechanisms. How do we differentiate between the two? Well, you send requests to the web server for pages, get information. That's why we have HTTP here as well. Both have ASCII commands and response interaction and status codes, which I mentioned here. And in HTTP, each object is encapsulated in its own response message, whereas SMTP, multiple objects sent in multi-part messages. SMTP uses persistent connections. HTTP has both, persistent as well as non-persistent. In persistent, once you have, access to your mailbox, once you are connected over it, once you have a connection made, all the transfers that would happen between, your mail, inbox, compose, and so on, that would be using the same connection. As compared to this, if you have HTTP's non-persistent connection, For each transfer, for each download of an object, you would require a specific download. You would require, each one would have one download between the two. Means one connection, one object to be downloaded. For each connection, you would first need to make a connection. All right. Like we saw in HTTP, the format for get and send these messages. Likewise, we have a mail message format in which we use this protocol for exchanging messages. We would require to have two things. One is the header, another is the body, as is mentioned here. And the RFC A22 defines the syntax for email messages. The header would have header lines, for example, to, from, and subject. And then we have the body of the message, wherein you type in the message supposed to send to the destination. Now, in this picture here, you can see that when Alice is communicating with Bob, Alice used SMTP to communicate with its email sender, the server. And when Alice's email server communicated with Bob's email server, it again used SMTP. So for the delivery, for the storage of email messages to the received server, it uses SMTP. Whereas Bob, while retrieving emails from his email server, might use some other protocol like IMAP, which is Internet Mail Access Protocol, defined in RFC 3501. So messages stored on server can be retrieved with the help of a protocol like IMAP. So if you have certain, applications which are email clients, for example, you have installed an app which helps you in it, then in those cases, those apps like Outlook and so on can retrieve using IMAP, POP, and so on, these protocols. However, you can use your browsers as well to retrieve the message, like you log in using HTTP, gmail.com. So Gmail, Hotmail, Yahoo, all these provide web-based access also to retrieve and send the messages. So in this case, what happens? HTTP comes on top of SMTP to send messages. HTTP comes on top of IMAP or POP to retrieve the email messages, in case you are using the web browser as a client. Do you get this? Any questions regarding email services? In fact, you can make your own email service. You can have your own open source email service or open source email server. And then there are a lot of them, like Open Exchange. The one which I have used is Squirrel Mail. Okay, there is Zimbra, there is Horde, Scalix. There are a lot of these, what you call email servers which are freely available there. So you need to download, you need to install. So with that, what you would do is you would create your own mail server. Once you have created your own mail server, you can then send and receive mails, and you can have your own name for that email server as well. The next application layer protocol that we'll be studying about is domain name system, that is DNS. Now, why we are sending? Because we would just generally need to understand, lower layer protocols as well. We took two services. One is TCP based service, both of them being TCP based services. Now let's talk about domain name systems. Now, as an example, if I tell you that to go to this website, type in 192.168.17.55. Then I tell you, okay, go to NIT website, type in 172.64.56. So on. Every time if I give you an IP address, it would be very difficult for you to remember that. As a human being, you would prefer something which is easier for you to remember. If I tell you this is Yahoo, that one is NIT, SRI.net, what would you do? It's easier for you to remember. In that case, we use naming methodology which we call as domain names. Domain names are simply, equivalent names for an IP address. You have nit3.ac.in, we have an equivalent IP address for that where it's stored on a web server. Now in this case, we would need services from certain servers who would provide us an equivalent IP address. Now, since you don't remember the IP address, you just remember the domain name nitc.ac.in. You would require service from some server who would change the domain name that is given by you into an equivalent IP address. Then only you can send your request for, let's say, connection or the page, whether it's HTTP GET request or whether it's email request. So we would need a server to map your IP address and the name, as well as the reverse of it, the name with the IP address. This server is known as domain name server, and this is known as domain name system. And the services that DNS provides is host name to IP translation, also does to the alias names, not just for HTTP, it does mail server aliasing, as it does load distribution also. Also, we have domain name system which uses distributed database, means which is implemented in many different servers. You have domain names 1, 2, 3. Even when you configure your IP addresses and you have to give domain names, you would have server 1, server 2, server 3 typically. There are several reasons for it. Why do we have distributed databases with respect to domain name system? Why don't we have a single domain name server here? The reason being, the first one, as the single point of failure is not there. That is, in case the DNS server fails, whole of the system would fail. If you have distributed, if first one is failed, you can try second one, you can try primary DNS, you can try secondary DNS, you can try tertiary DNS as well. There will be DNS which will be provided by an internet service provider. And also there are free DNS, which are many of them which are available around. You can just Google them and you can find what are the free DNSs. The second is that if we have a centralized DNS, all the traffic would go to that DNS. So there would be, a lot of traffic flowing to the same server, and it would cause delays. That's why we prefer having, decentralized distributed DNS. Then if we have a centralized database, let's say somewhere in, let's say, US, you can imagine how much time it would take us for sending as well as retrieving the how much the RTT would be for that centralized database. It would be very distant from where you are sending. And because of the large volume here, it would be difficult to maintain. That's why we have, which I mentioned in the previous slide, we have a distributed database implemented in many of name servers, hierarchy of name servers. And what is the hierarchy here? I said there is primary, there is secondary, there is tertiary DNS. So an example here is Comcast DNS servers alone has 600 beads of DNS queries per day. So this is how the distributed hierarchical database of DNS looks like. We have a root DNS server, then we have DNS servers with respect to each of the domain name. What we have top level domain names like .org, .edu, .com. And then within each we would have authoritative DNS, which is given by, let's say, .com, yahoo.com, amazon.com, and so on. And likewise, we would have for edu.org, .gov, and so on. So this is how hierarchical would work. So if a client wants the IP address for an equivalent domain name, which is amazon.com, first approximation would be client queries to what? The root, which is given here. And then the root would query its .com server. And within this .com, it will get the DNS, the IP address of this domain name. As mentioned here, there are 13 logical root name servers worldwide, and each server is replicated many times, around 400 servers in US itself. So this is basically the hierarchical structure of the DNS. The root DNS here is mentioned that it's the contact of last resort by name servers that cannot resolve names. And then we also have, as mentioned here, top level domain names as well as authoritative domain names, which is mentioned here, where top level is .com, .org, .edu, .aero, .jobs, .museum, and so on. And also there will be top level domain names with respect to each country, like .in, .uk, .fr, and so on. Then authoritative DNS is organization's own DNS server, which can do this, which is maintained by organization or service provider as well. If you have BSNL's service provided, BSNL would give you an IP address, which is BSNL's own DNS server, which comes here at the last as authoritative. Now, like I mentioned, for email services, we can have open source, email server created by you. Likewise, there are, open source DNS servers which can be created. In fact, there are plenty of open source, there are free DNS servers which are there. And in this case, if you want to create your own DNS services, there are OpenDNS. Okay, you can build your own DNS name server on Linux itself. Okay, you can use Bind to develop your open source DNS service, Bind is for Berkeley Internet Name Domain. And it's not that difficult. Setting up a DNS server using Bind is pretty much simple if you do it on Linux-based services. And nowadays, in fact, having Linux also is not that difficult on Windows. Why? Because there are lots of protocols which help you in installation of Linux or Windows. For example, in our lab, some people had difficulty in, certain commands in Linux because they had Windows. If you had Windows 10, it was not that difficult to install this, Linux. Why? Nowadays, you don't need to double boot, dual boot. You don't even need, open a virtual box or VMware like things in which you would want to have two operating systems running parallel. There is WSL, which is provided by Windows 10, in which you can easily have Linux installed over Windows and you can run all the commands, the app, and so on within that Linux application. So I just mentioned it here how it can be done. There is WSL2, in which Linux can be put in Windows itself. And it's easy and also doesn't take much of your space, and it's not and it's not having that much of overhead because you are not using a dual boot, you are not using, in fact, a virtual machine to install it. So the overhead there is lesser. So I was talking about your own DNS server here. So you can create your own DNS server by using Linux. How would it help? Now you can create a local cache of the DNS. For DNS first, you would need to query it and get back the result. So if your DNS server is a number of hops away and you create your own DNS server, which is one hop away or two hop away, and once you start building this DNS server, the recent or the mostly used DNS would be stored there. It may be updated regularly. Out of date would be taken out. And slowly, you will have a very good local DNS server, which would overall help you in saving up of time. Any questions? So how to get the reply of DNS here? Firstly, how do you know the DNS server? Your emails, your ISP has provided you, for example, the IP address of DNS server. If you are getting manual configuration or you are putting DHCP for your IP address, then with this IP address, you get several other things. You get IP address, you get netmask, you get default gateway, and you get primary and secondary DNS as well. So you would have these details available there. Next is you want to go to a website. Let's say there is given an example here, engineering.nyu.edu. Wants an IP address for cs.umass.edu. So what would be the steps that it would do? So the host would first request the local DNS server for the IP address of it. The local DNS has two options here. There would be either a hit or a miss. If it has this available, it would reply back. But if it's not available there, it would go to the root DNS server, saying, I don't know this name, but I'll ask the server. Then the server replies back, giving the server where this would be available. Then this TLD DNS server replies back. So first the root tells where to find this .edu. Then .edu replies back saying that this is the authoritative DNS server where dns.cs mask is available. It replies back then giving the exact IP address of the page where gaia.cs.umass.edu would be available. So this is basically an then iterative query that we have. And once the authoritative DNS of umass.edu has replied back, then only it can get back. Then only it can access the server. The second one that we have is DNS name resolution using a recursive query. Again, they have the host which requests for it. It queries the local DNS. And the local DNS goes to the root DNS. The difference here is that root DNS would reply back to local DNS. In the previous one that we saw just now here, two, then we have three replying back to it. This is where we had iterated query. But in case of recursive query, we have all the burden put on the for the name resolution on the contacted name server. So you tell me how to access it. So root DNS goes to TLD DNS. See the difference here? See here, root DNS in iterated replies back. Then it goes to TLD DNS and so on. However, in case here, we have in recursive query, local DNS accessing the root DNS server, and it leaves the burden of it for them to find out what is the top level domain name server. Here we have number 3, and TLD would go to number 4 for authoritative DNS, and then it replies back to TLD replies back to root replies back to local, and local gives back to the requesting host. This is what we have as a recursive query. Like we had in previous one, cookies as well as caching. So we have caching and updating of DNS records here as well. There are local DNS servers here, as is mentioned here. Once you get the address of cs.umass.edu, your local DNS would cache this, DNS name here. Now what happens is next time when you or somebody else using this local DNS server access same umass.edu, the domain name query equivalent IP address can easily be got from this local DNS server. It would be a hit. It will not be a miss. This would save an overall time. You would see it would have a look the lesser RTT of not sending the request from local to root to TLD to authoritative. This is where caching of DNS helps. And also, it would require certain updates regularly, by which if there are some which are not available, out of date entries, they need to be taken out or they have to expire from the DNS name resolution. So how does the DNS record actually look like? DNS are distributed database storing resource records, RR. They are using RR formats in which we have a name, a value, a type, and TTL. The first one, that is the name, that is the host name, nitcity.ac.in. Then we have a value, and the value is of IP address. That is the equivalent IP address that we have. So this is the DNS protocol message in which we have a query and a reply. and both have same format. So DNS query and DNS reply would look similar. The records that are saved, these are saved in as MX records. Okay. So we have MX records in DNS server, where MX is a mail exchanger record which specifies the mail server responsible for accepting email messages on behalf of a domain name. Is basically a resource record in DNS. We can record several MS records for emails. So if we have type here, you can see format here. First one is name. Let's say I'm saying mail.nic.net. Then we have a value here that will give the IP address. Then the type here, if it's MX, the value here MX would mean that it is a value that is associated with a mail server. I'm checking a mail, that means MX here. And TTL would be the time to live, for how long this record would be maintained. Need to refresh at regular interval. The format here is given with header as well as the certain other fields with it. Header given by the identification and flags. Then we have the questions, answers, authority, as well as additional with respect to this. If you want to have your own DNS domain name, you would need to register it. Okay. And registering a name is done at DNS registrar. You'll say that, okay, this is my, DNS name. I want to record my DNS name with this. And then you will give your equivalent IP address, that this is the address where this name should direct to. Then within that address, we expect that you would have your web space. And within that web space, you would have kept your files. Let's say nitcity.ac.in. So it was recorded in the DNS registrar within ac.in, which is an academic institution within India. And NIT is the domain name or the host name. Once you click nitcity.ac.in, it would direct you to an IP address where we have kept the files, where we have the web space, where we have the web server. Within the web server, there will be a lot of pages, let's say, for example, index.html. Now, this DNS registrar would have insertion with have record of whose DNS name is it, to whom does it belong to, and who's the owner of it, to whom it should be contacted in regards to this. If you go to several websites in which you want to see, check who in whose name, nitc.ac.in is, you can go to a website and check in whose name this record is. When we have the DNS security, we will not be taking that within this. The last part that we have here is P2P applications. The common P2P application that all of you would be knowing is BitTorrent, that you use for file sharing and file downloading. I'm not sure whether it's accessible from campus or not, but I believe it might be blocked. So P2P sharing is the third part of we saw the first one as the client server, right, in which we have messaging, we have HTTP and so on. Now we have P2P, in which we have an architecture which is, you know, typically a hybrid between the two. Now what is P2P? Basically, we would have a peer requesting a file from another peer rather than the server here. Okay. We do not have a server here. We would request between each one of us. And it's like I'm requesting some file from you and you are replying back that file to me. You're not a server, you are a host by itself. You are yourself an end user. So each one of us combine together and we share files directly between each other. This is what we have as a peer-to-peer architecture. We can be connected together all together, or we can have connectivity intermittently. We use the intermediate IP cloud to communicate between each other. We have a file that can be distributed among a number of users, and each user would provide us a part of file that can be file distribution within P2P. If we compare this with a client server architecture, like we use FTP to download a file, the whole of the file we expect to be on a single server. Whereas we are not using here a service of a server. Instead, we use a file which is distributed across many of the clients. This shows the difference between the two. Also, an example of BitTorrent is given there. I would leave that for you to discuss about these. Do we have a question here? All right, Ramanand, this should be the end of our course. You can stop recording here.